x squared plus x plus 1. All right, let's try and let x go to infinity and see what happens. So the numerator, 3 times infinity is infinity plus 1. Infinity plus 1 is infinity, right? Divided by infinity squared plus infinity plus 1 is all infinity. Square root of infinity, still infinity. Does that make sense that that would still be infinity, square root of infinity? And let's just try and get our heads around this. I mean, in the previous class, we saw that when you get things like 0 over 0, sometimes that, it heads towards a number. And here we're seeing that when the top and bottom try and become huge, sometimes they actually make a compromise and head to a certain number, like the previous one was negative 0.75. So does this head to a number or not? Well, the idea here was the same as the other one. Let's try to eliminate the highest power of x in the denominator. So what's the highest power of x in the denominator? X squared, right? So I need to come into the front of this, and I left some room here, with the 1 over something and a 1 over something here, right? Now I'm showing this example because it's a little tricky. That 1 over something has to be put in front of the root. You can't put it inside the root, because if you put it inside the root to start, then the top's not under a root, right? So whatever you put has to be in front of both. Then you have to multiply it through. So what happens if you try and multiply something into a square root? Here's one way to think about it. Let's say I had square root of x cubed. Isn't that the same as square root of x squared times x? And what can you do with that x squared inside of it? You can take it out as an x out in front, couldn't you? Like this? Most students are comfortable with that. What students don't usually see is how to force something back in. When you've put something on the outside of a root and you force it into a root, what happens to it? On its way in, what happens? It gets squared, right? If that was a cube root and you try and force something into a cube root, then on its way in it gets cubed. So whatever I come up with out here, that 1 over something, I have to keep in mind that when I force it into that root, it's going to get squared. So what should I use? 1 over what? X. 1 over x. Because when I force that inside, it's going to become a 1 over x squared when it goes in, as opposed to a 1 over x. Now, is it going to turn into an x squared on the top? No, because there's no square root that I have to pass through. Yes? That x squared can't come out because it's addition, not multiplication. So like over here in the problem that I did here, the reason why this x squared came out is because that's multiplication in between. If it's addition, you can't. Is that all right? All right, so let's go ahead and pass the x 1 over x through on top and bottom. What do I get in the numerator? I mean, don't let x go to infinity yet. Just tell me, algebraically, what's 3x over x? 3 plus 1 over x. Okay, in the denominator, I still have the square root, right? Some people, I've been teaching for a long time, so for some reason people will forget the square root. Like they think it goes away. It doesn't go anywhere. It's still there, square root. When that 1 over x goes in, it becomes 1 over x squared, and it passes through to all 3 terms. So what would you get down there? X squared over x squared, which would be 1, and then plus x over x squared, which is 1 over x, and then plus 1 over x squared. Remember, when that 1 over x goes in here, it becomes a 1 over x squared, and so it's got to multiply, oops, it's got to multiply times this, this, and this. All three of them get x squareds below. Now let your x go to infinity, and what happens? Vanishes, 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 because you got fixed over infinity on those, don't you? What's left? On the top, 3, bottom, square root of 1, but the square root of 1 is 1, right? So your answer is 3. So there's some algebra there involved, right? Now I'm going to let you take your break, but hold on. I know you really want to take a break. I do too. Okay, the infinity symbol. Anybody know where the infinity symbol comes from? Well, there's several different arguments as to its origin, but have you ever seen a Mobius strip? A Mobius strip, oh, son of a bitch. There we go. Okay, this is a sheet of paper, right? We could argue that this thing has two sides, right? I mean, you got the side with a little bit of writing on it. You have the side that doesn't have any writing on it. You'll see it? Now, you could argue that, yes, there is an edge along here, an edge here, and those are sides. But just generally speaking, people would say this is two-sided, correct? Okay. If you take this strip of paper and you twist one end and you put it back upon itself like this and paste it together, then this is called a Mobius strip. And this is an example of a single-sided surface. So if you take my index finger and my thumb, they are actually on the same side of this surface. So you follow the index finger around, come back, you'll be on your thumb. You come back around, you'll be back on your index finger. So there is no two sides anymore. It's all one side. So you can almost kind of see the idea of infinity here. As you walk, imagine you're a little ant, right? And you walk, you just keep walking, and keep walking. As opposed to this, where if an ant walked, there'd be bounds. Does that make sense? So that's one argument for the idea of the concept of the symbol, but that's not why I put this up here. Because that little commercial with the blowing up heads and stuff, there are two types of infinity. There's what's called countable, and there's what's called uncountable. Now, an example of countable would be all the integers. 1, 2, 3, 4, forever and ever. If I told you just start counting, right? This was another conversation I was having with a child at a Father's Day thing yesterday. And I'm trying to explain the idea of, like, you can count forever, right? You can just sit there and count. There's no biggest number. You just keep going, right? That's countably infinite. What's that? About 10. Yeah. So, but there's a systematic way to pass through the numbers, right? And another example of a countable set are all the fractions. If you take every fraction on the number line, okay, look at just the numbers between 0 and 1. Okay, so I'm just looking at that interval and just the fractions. So all the fractions in here, like 1/2, here's 1/4, right? There's all these, what, 2/3 is in there somewhere. Well, actually, it's on the other side. But you know what I'm saying. All the fractions in there. There's a way to start at 0 and walk your way across the number line from 0 to 1, going through all the fractions like lily pads on a pond, walking across. You'll never get to the other side, though, because there's an infinite number of fractions. But you can start walking from one side to the next and never and make progress towards the other side, but never get there. Does that kind of make sense? So it's like you step off the edge, you're on a lily pad, you go to the next lily pad. Here's my little lily pads. All right? Except that there's infinitely many, but you can start counting across. Those are all countable sets. Uncountable is if you take all the numbers between 0 and 1, including irrational numbers, which are the things that are not fractions. Then you get what's called an uncountable set. And there's no way to even start to systematically count your way through. So it's kind of like if you started at 0 and said, okay, I'm going to step to the next number. Here's the lily pad, right? Here's the first lily pad. I step to the next one. Not only will you have missed lily pads, you will have missed an infinite, uncountable number of lily pads. So you try and take a step back, and you realize you just missed again another infinite, and then there's just no way to count through them. So all the numbers between 0 and 1, if everything in there is uncountable. The fractions between 0 and 1 are countable. So those are two types of infinity. And the best analogy I have of this, and I love to share this story, is, and you can use this if you'd like, next time you're, spring break or something, you're walking on the beach at 3 a.m. with someone else, maybe, and it's all dark outside, right? It's all dark outside, and the beach is on there, right? Here's the waves and stuff, and you're talking about, uncountable and countable. Then if you look up into the sky, at a dark night away from the city, you see stars all over the place, right? Everywhere you see stars. That was a shooting one, yep. So all these little red things are stars, right? And there's a bunch of them. You could almost look at those as like the fractions. They're all over the place, right? There's so many of them. You start trying to count them, and you could maybe start counting your way through the stars in the sky, right? But you're going to pass out before you get through, right? Okay, that's the fractions, countable. The black is the uncountable. Those are the irrational numbers. And those are like examples of irrational numbers, square root of 2, pi, e. You're usually taught that those are irrational, but no one ever tells you that there's so many more irrationals than there are rationals. So everyone thinks that, oh, there's only a few. It's actually the opposite. So if you just think, someone says, okay, start counting stars. You're like, sure, okay. 1, 2, 3. And then they say, start counting the black. You can start, you try start, then where do you go? It's just everywhere. It's super dense everywhere. Does that kind of make sense? Okay, I'll share one last thing, and I'll make it, I swear, less than a minute. When I was in graduate school, I used to have, how many of you are going to go to grad school? Yeah? Okay, so you'll probably find when you go to grad school, you don't really have a whole lot of time for anything else. Like socially, you're going to be doing nothing, okay, except whatever it is you're studying. And so when I would go out every once in a while, I would like to go to these clubs and dance and just like sweat out all my frustration and like confusion, right? I just go get, you know what I'm saying, right? So I would go to this club that I always go to, and if I ever had a night where maybe I met this girl or something, I always had a question that was like my standard bar question, like, this person has to know some math, or else I can't even exist right now without doing math, right? So my question used to be, if you look at the interval 0, 1 and reach in there and grab a fraction, reach in there and grab a number, what's the probability it's a fraction? That used to be my like standard, hi, how you doing question, right? And so the probability